Welcome, ladies and gentlemen. We want to help you to prepare for the future of mobility systems. But how does the future of the automotive industry look like? What are the aspects, or better, what are the enablers to make that future happen? First, let's have a look in the automotive trends that we currently see. Well, the future is automated, it's connected, and it's electrified. These three aspects opens the door to the new user experiences. And it's the prerequisite for shared mobility. Shared mobility with driverless vehicles, which is a game changer, since it may dramatically reduce the number of vehicles that are required in the future. I'm sure that we will see the transition towards the shared mobility, but no one really knows when and to which extent we will experience it. Anyhow, everyone who wants to be in the business needs to have the ability to develop these new vehicles. And I want to talk about what enablers do we need to handle to make that future happen and what is required to enable you to develop these vehicles. We do see a lot of changes in several aspects, and today I'd like to highlight some of these aspects. When considering the aforementioned automotive trends, what do you think? Are we prepared for them? Do you think that the current EE architectures and the ECU types are sufficient? Or do you already know how software architectures may look like in the future? Also, are our collaboration models still up to date? A lot of questions, a lot of open topics, and I want to give you some insights on what we are currently observing and what we are currently working on at Vector. So let's recapitulate and rethink those enablers, the EE architectures and the ECU types. That's the first thing that I want to focus on. Are our EE architectures and the ECU types sufficient? What did we see in the past? What was the progress until today? And what we see currently being used? And how could architectures look like in the future? Let's get and dig into these details. We are coming from an architecture where the ECUs were distributed around the vehicle. So we had a very distributed architecture with a lot of small ECUs. These ECUs were implementing a dedicated function. Typically, they are having their own sensors and actuators if they need some. Whenever adding a new function, a new signal was needed, which in turn changed the whole communication matrix. This led to the drawback that this design was specifically for one vehicle, and it made it very complex and expensive to extend the functionality. What was the next step? How to overcome those issues that we see in such an architecture? Well, this directly led to a change where the functions have been aggregated according to their domain usage. So we figured out that clusters would help to already consolidate ECUs into bigger domain controllers according to their function they are contributing. In these domain controllers, software from multiple vendors was used and they shared already sensors and actuators. So it was a better structured approach. But what issue came with that transition? Well, the new functionality is requesting an interaction of different domains, like for example, the park assistant relying on the infotainment as well as on powertrain informations, for example. This is more or less where we are at the moment, a domain-centric architecture where we see according to the functional clustering. But as you can see, there are still issues in it. And what could we do to overcome these issues? What's the next trend that we are currently observing? Well, the next trend is a so-called centralized architecture. In this new architecture, we see three types of ECUs. What you can see in red are the commodity ECUs like sensor and actuator ECUs with a very basic functionality and little variance. In blue, we see integration ECUs, which can be domain-oriented, but we see more architectures with a zone orientation. This means we are not having a look into the integration ECUs from a functional perspective, but from a perspective where the ECUs are located within the vehicle. And on top of these two types of ECUs, we see the high performance nodes. And those high performance nodes typically rely on system on chips or microprocessors accompanied by microcontrollers. And this is the trend that we are observing, but directly leading us to the questions, how will these brain ECUs look like regarding their software architecture? What do we actually see in it? Well, comparing those and sum it up how the ECU types look like. First, we do see the sensor and actuator ECUs with a very basic functionality. Then we see the integration ECUs with lean or rich functionality, and then the vehicle brains. And the vehicle brains are those ECUs in the vehicle which are the focus for the innovations and for the competitive differentiation. That's the trend that we are observing. Those are typically also linked to the cloud. They are communicating with your backends. They are sharing information. Those are the main focus that we are going to have a look on today. And therefore, let's have a look into the software architectures and what is required for such vehicle brains. How may the software architectures look like? Let's recap the software architectures that we are currently using and what will come up next. So let's have a look at the software frameworks and the software platforms. Today, a lot of them are based on the classic Autosar world and managed by typically the tier ones. This is true for very many of the ECUs that we have around in the vehicles currently. Looking at the basic software, we can see a clear dominance of the Autosar Classic, a bit earlier in Europe and a bit later in Asia and North America. But this is not the only thing that is used and that will be used in the near future. Now let's see what the three kind of ECUs, the three types of the different ECUs that we've just seen can utilize for the software architecture. Classic is the right basis for the sensor and actuator ECUs. Beyond this, we see a usage also in the integration ECUs. And not to forget, in case of fail operational, we will need the classic as well in the brain ECUs. The classic world is quite static and it's designed as a monolithic system. Its main goal is to achieve the maximum efficiency. The classic world is developed in C, it's quite static, it's model-based, and it's configured at compile time. The main field for adaptive are the vehicle brains, but depending on the feature content, it can also be useful for the integration ECUs. Adaptive is intended to provide maximum flexibility based on a very dynamic and modular approach. This is typically developed in C++, also model-based and software-based, and you're configuring it at runtime. So there's a huge difference compared to the classic world. Targeting most of all the vehicle brains. Now, one remark that I want to make is the communication between these two worlds. The communication and the seamless integration between these different portions is ensured by the Autosar methodology. It is based on one comprehensive communication design. This is a clear trend that we see that those controllers and ECUs based on these new controllers like microprocessors or SoCs are making use of the adaptive Autosar standard. Depending on the feature set, this can be in combination with other partitions like, for example, a Linux system or an Android system. The preferred release for Autosar Adaptive is release 2011. Well, Adaptive Autosar is still quite new, but it's already a mature standard. But what about the market penetration? It is already used in some of the production projects. The first SOP is in the Volkswagen ID.3 in 2019, and we see an upcoming version of the adaptive Autosar with safety requirements in BMW's iNext. And there are a lot more production projects which are not yet public. And not to forget, we see increasing demand for prototyping and evaluation projects. So we are convinced that we will see a lot more from adaptive quite soon. Now, we have seen the basics about the architectures and where they could be mapped on. I mentioned that for the vehicle brains, for example, we see a trend that not only adaptive, but a combination of adaptive and classic might be useful. How do we map that on such a new or modern SoC architecture? Well, let's go into that details. The SoC architectures provide typically two kinds of processing islands. The one is a microprocessor island, and the other one is the microcontroller island. In the microprocessor island, we find powerful processing cores, allowing to compute a lot of data and applications, while the microcontroller island is better suited for real-time processing and safety applications. Hence, the functions are split according to their needs and mapped to the according architecture. Examples here mapped or connected to the adaptive world are the radar, LiDAR, or camera-based functionalities where we do have a lot of throughput of data, where we need to process quite a huge amount of data that is handled in a short time frame. On the other side, we see then in the classic world on the microcontroller island, then basic features and safety supported features like, for example, braking aspects or stuff like that. However, depending on the functionality, there is a need for a communication between the adaptive application world and the classic application world. And for that, we need an interprocessor communication interface. In case of an SoC, this might be realized with a IPC in the shared memory. In architectures where we split it up, it might be different. We'll have a look on that later on. But now let's have a look on the software architecture. How do they look like? Well, on the microcontroller island, we find MPU-based controllers with a bare metal operating system in the Autosar Classic environment. And those are built up within one single binary, so it's a monolithic system. On the microprocessor island, we do see hypervisors used as a standard part of the software architecture. This allows us to use multiple operating systems and separate them, for example, due to safety or security reasons from each other. There we see the individual app binaries. So it's not built up as a monolithic system. It's more, we do have small apps all coming in a separate binary. And to have a benefit out of that, communication is also dynamic. We can add new apps, communication is adapted. We can remove apps, communication is adapted. So we have a very dynamic behavior here. Let's have a look what happens if we go from an SoC, from a system on chip, to a microprocessor architecture accompanied by a microcontroller. As you can see on first glance, not too much is changing. The software architecture actually does not change in that case. We still have the adaptive world running on the microprocessor islands, and we have the classic world running on the microcontrollers that is accompanied. However, what changes the interprocessor communication interface? We cannot rely anymore on the shared memory approach. We need to have an implementation based on external bus systems like, for example, SPI or PCI Express. Well, getting back to the overview, at a first glance, that architecture looks rather simple and straightforward, but there are quite some pitfalls. Let me just point out one of them. Security. What about trust in such a system architecture? Well, security is handled in very different ways in the microprocessor and in the microcontroller island. While in the microcontroller island, typically a dedicated hardware component is present, so-called HSM. On the microprocessor side, only a virtual trust anchor is available. Such virtual trust anchors can, for example, be a trust zone, which is also able to access hardware accelerators to improve the performance of the cryptographic operations. Second thing that is different on the microprocessors, the operating mode which the chip is in is defining how the accesses are allowed. The isolation between the trusted and the non-trusted partitions can be achieved by using these different operation modes set by a hypervisor. So the hypervisor can provide trust boundaries. But the access to the crypto services during runtime is just one aspect. It's not only what you're doing during the ECUs up and running, it's also a question about how to start them up. So what about secure boot? What about the key handling? All questions that needs to be answered, especially in these new processor approaches. We are in these discussions, we are thinking about possible solutions, and we would like to discuss that as well with you. By the way, security is not only a question with respect to the technical solutions, it's also an organizational challenge. Let's have a quick look and excursus on that topics. What are the new challenges for cybersecurity? We already saw we have very open and connected systems, which means that we do need to protect more and more external interfaces with respect to security. We have less encapsulated systems and more flexibility for updates. And this directly belongs to the question of vulnerability handling. How do we report them? How do we fix them? How do we roll the fix out? Then we do have introduction of more sophisticated security concepts. And I'm not only talking about security protocols like TLS, IPsec, or MACsec, which will also come up in the near future. It's also about intrusion detection and prevention systems. This means those questions are not within only one single ECU. Those are very distributed security approaches. So we have the security more and more also distributed around the ECUs and the vehicle architecture, and also having an influence to the backends potentially. And we see that also the upcoming standardization and regulation, like the ISO 21434 and the UNECE, will have a huge impact on the organization. We see that there's a demand for security awareness, and we need to align our processes as well for the development, as well as, for example, the vulnerability handling and stuff. But security is not the only pitfall that we find in such systems. Since it's very related to safety, I will also give a brief overview on what the safety aspects are when having that changes. What are the challenges for safety in an adaptive context? Well, we see very dynamic and flexible systems, which are very hard to verify. Decisions are moved from the configuration time to runtime, makes it more complex. We have very divergent requirements of ADAS and infotainment, for example. We have much more powerful hardware, which provide typically less safety mechanisms. So we, for example, do not have a possibility to recognize random hardware faults in them. There's a lot of new non-automotive players coming into the market that are also maybe not used to that. And maybe it's not required because we can accompany it with a microcontroller as well to cover the safety aspects. Then we see the fail operational systems. We see that it's not possible to shut off the system in any case in the future. We need to have still some basic functionality available. This is a new type of safety requirements. I give a brief update on that on the next slide as well. And we see also the introduction of a new complex technology in the automotive world, C++ programming language. It's not that easy and straightforward as it may look like in the beginning. We have new coding standards that we need to align for, and we have new compilers and new analysis tools that are required, that need to be qualified in order to be used in safety projects. But let's get back from this process and organizational perspective to the technical one. I'm more the technical guy, so let's have a look back on the architecture. What does it mean for our ECU architecture with respect to safety? Well, the microcontroller island is much easier to verify. It provides better fit rates as well. We need less hardware redundancy to achieve a certain ASIL level. This is not surprising, right? This is something we know from the past. These microcontrollers, or the microcontroller islands, typically host the classic Autosar stack, where we are also very confident in the safety aspects. But don't get me wrong. In fact, we are also finalizing our ASIL-D adaptive stack. But there are different types of safety requirements. Let's think about one example, the highway pilot. There are parts that always need to work no matter what happens. And this results in a safety-related availability requirement. So it's not safe anymore to shut it off. We need to make sure it's still available. On the other hand, fail-safe software may stop working and switch to a defined safe state, which is quite fine, depending on the safety analysis and the safety concept that we are going for. But still, some pitfalls exist, especially within the operating systems. But to sum it up, there are two different types of safety that need to be considered while doing that split. And also a safe communication between the parts is required. By the way, I just talked about fail operational. The fail operational solutions for classic Autosar is already on track. The adaptive is in planning. So it's something that we are actively working on. Well, an adaptive is a quite good keyword. So let's figure out what it is about and what potentially comes beyond adaptive. Well, adaptive Autosar is quite good basis for the development of the user applications. It has standard interfaces. Some OEMs are developing or at least discussing an extension leading to a system that we call software runtime framework or vehicle operating system. In between the user applications and the hardware, we have exactly this runtime framework. It consists of the adaptive Autosar solutions and extensions like, for example, framework apps for security and so forth. That absolutely makes a lot of sense. The only remark that I'd like to make here is the OEMs should avoid differences that are not useful and not needed. This will save costs and reduce the time to market for all of us. But now let's think about the combination that I mentioned before. Very complex systems integrating both worlds, the classic and the adaptive world. How does that get together? Well, beyond that software frameworks, we see a trend to the transition to a so-called software base layer. That's how we call it. This base layer represents the runtime framework for the OEM in-vehicle functions, including over-the-air use cases. It includes the safety and security handling for the OEM and also some other basic apps that are common for the vehicle and the OEM. Furthermore, it contains a set of basic software modules which are required in the OEM's typical use cases. This means we have a more standardized set of elements and components within the basic software that are used for the OEM ECUs. And this is valid actually for both the classic and the adaptive world. That's why you can see it here as well. What else you can see here is a potential work split. How could that work split look like? This is a discussion that we are also in at the moment and a trend for the development that we see for the ECU software. Well, I talked about the user applications and the software base layer, but what comes beyond that? Is that all that we need? Actually not. So what else we need is a so-called software development framework, like for example, a vector adaptive Autosar development framework, which allows you to design, configure, and integrate all the software that you need. So this also requires a tool set to develop the ECU software. Tools that allow also high automation and ask for user interaction only when really needed and necessary. This can be seen as the software development framework. But is that all we need? No, it's still not. In addition, we need a software platform architecture to support development for a large variety of projects with a maximum of reuse potential. This sounds very easy, but in fact, it is a real challenge that needs quite some upfront invest. And it needs strict discipline and a good strategy for especially reuse, update, and merge. But did we cover already everything, or is there something else? There's another aspect. It's a so-called software platform development framework. We need tooling to manage the whole software platform, and it's not about the source code. It's about supporting different specification levels, like an engineering backbone, support of platform management, and also supporting parallel working on the artifacts. Very important topic. Do you think we covered everything right now? I still don't think so. There's another one, processes and organizations. I mentioned that already in the excursus. We need to make sure we are working in an agile development manner, and we need to make sure that the safety and security processes are aligned. And as you can see, it's quite a lot of work, a lot of topics that we need to keep in mind. And hence, this is something not each of you could do alone. I think this is something we need to collaborate. And that's exactly the next enabler that I want to talk about. Are our collaboration models up to date? What is required and what do we need to consider when developing software together? Not only each of us independently, but together software development. What is required in that case? Let's go and have a look into these details. Software will drive the future, and the roles and the responsibilities will change. So we are observing changes in the responsibilities for the software development. On the one hand side, we see OEMs taking over more responsibility for their software in the ECUs and starting to develop functional software on their own. This comes together with the integration responsibility of the software. On the other hand, as mentioned already, we see still increasing complexity with respect to the ECU projects, complex hardware, powerful hardware, a lot of processing power. This also requires a more powerful development environment as well as continuous integration and deployment. This may also increase the gap between software developers and the hardware. Software developers will implement against a standardized software interface, not caring about the underlying hardware, more IT-like software. And these changes lead to a redefinition of the roles in the software development. From our perspective, the role of the Tier 1 may change, and also the cut within the ECU development for the different roles will happen, for the integrator, for the function developer, for the framework provider. And for that, we see the need for collaboration models. But how to enable these collaboration models? I like to remark that we need tools to support it. Without these tools, we will not be able to efficiently collaborate. Hence, let's think about these tools. What are challenges for the Autosar tooling world? Well, as mentioned, we see the complex heterogeneous systems, where as a result, Autosar Classic and Adaptive will need to coexist. We need to cope with that and the tooling. Now, different parties are contributing to the development. Hence, we need to share artifacts across the organizations and support a horizontal software integration, which means we have to share different artifacts across organizational units and need to work all together on one software stack layer. And we also need support and ways for individual local integration and for global merge to cope with the feature-driven development. Finally, we need to have continuous software development. We need to increase the degree of automation to make sure we are faster. And here we are talking about shortening intervals for the integration from months or weeks down to hours. And this is only possible if we have the according automation in place. How could that look like for a whole process? Well, what we like to do is we like to develop very generic application software, which is platform and project independent. As an additional artifact, we have the system design, the EE and the software architectures, API designs, and the ECU platform deployment. And now we can put these two artifact informations in the according software architecture world. So we can split it up according to the functional needs into the classic development and the adaptive development. The classic IDE supports the app packages, the software component models, the code, the integration constraints. Same holds true for the adaptive world. However, the result of this classic development and the adaptive development is put into the according runtime framework for classic and adaptive. And then based on these two portions, combining them together in the continuous integration for classic and the continuous integration for adaptive, we have all the artifacts that we need to combine them to the whole ECU software. We can use the ECU platform deployment from the system design, put the continuous integration results for classic and adaptive onto that certain ECU. And then we can start the testing phase. We can perform the ECU software tests, and we need to manage the whole ECU software, like the variant handling and also the fleet management and the deployment strategies. When all that is done, we can deploy the results onto the vehicle, for example, via over-the-air updates. Collaborative software development, what does that mean? What aspects do we need to consider? Well, it's a software platform architecture on the one hand side and a software platform development framework on the other side. Regarding the software platform architecture, we need to make sure that we have a reasonable abstraction of the ARXML model elements for user-friendly comparison of changes. We need a good comparison mechanism and easy and semi-automized merge of changed artifacts from different feature branches. So we need to have like a 200% product where we are having a 150% program and a 100% ECU project, where then the resulting features are put into. We need to support the parallel development of different features at the same artifacts. And we need a clear and very good strategy for reuse, merge, and update. On the other hand, as mentioned, the software platform development framework. And this is a framework that needs to support the engineers over the different levels of abstraction and the different specification levels as well. So we need something like an engineering backbone. We need to have the support for the platform management and the support for parallel working models. We have a shared tool chain across the different organizational units. And the integration into different integration pipelines for each integration layer and organization. So we need to cope with the whole database in the end. What does that mean if we have a look at continuous integration and development? How does the steps are looking like? Well, we have plan, code, and build, three major steps. Then we provide the feedback to the beginning, so giving fast feedback during the development by automating the software creation already accelerates the development. In the past, we had only compilation and build automized, and the rest was actually manual work. Today in the future, we want to automate that, also the software configuration, the software generation, and the unit testing. As a side note, the option for the CI of the DaVinci Configurator Pro enables the automatic software configuration for the Autosar basic software with the changes. Well, this is the continuous integration aspect. What about the continuous deployment aspect? We are extending the continuous integration in a way at the end with a shippable software. This means we are adding to this continuous integration the testing aspects, functional testing, non-functional testing, regression tests, acceptance tests, and then at the end, the software quality is ensured in a way the software could be directly deployed to the car fleet, so directly rolling it out. And this has a benefit not only for the internal software development, where we are much faster, we are avoiding a waste of time during the development. It's also a benefit for the end customer because we are more quickly in the vehicles with the solutions, with the updates and the changes that we've made. Let's go into the view of different roles that are involved in the software development. Traditionally, we have a role-based working model. This role-based working model works with experts dedicated tooling where these experts are familiar with. Well, starting with a system architect using, for example, Prevision, working on the system architecture and handing over the information to the application software developer. Application software developer then subsequently develops the functionality with a tool support with dedicated tools for exactly that step. Afterwards, handing that over again to the integrator, taking care that also the basic software configuration fits as well. Maybe performing some preliminary tests in a virtual environment before handing over to the tester, which then brings everything to the actual hardware and tests in the system context. So the tools are typically used by engineers of a certain role. Mainly manual-based working is used in this traditional role model with defined work split between the different roles. How may that change for a modern ECU development? Let's have a look as an example to the application software developer. Application software developer works hopefully in the future with a very lightweight tooling, like for example only the integrated development environment, the IDE for writing the code. Optional, it can also use the developer, for example, for graphical visualization of the software components. And the IDE allows also to define instructions and customizations for automatic processing. For example, integration instructions. The results of his work are then committed into the version control, which is then triggering the CI server, so the continuous integration server, like for example, Jenkins or TeamCity. This is already triggered by the commit and starts the CI/CD pipeline. Additionally, the baseline is checked out for automatic integration, containing the basic software and the basic configuration. Then the CI/CD pipeline triggers several work steps, like for example, the input validation, the configuration, the generation and build process, the test and verification steps, the non-functional tests, and the reporting. So you see, this can already be automized in this CI/CD pipeline. But what are the requirements for the tools behind that? We need to have a good automation support via scripting, model changes, helper functions, import-export features. And we need to have a good reporting to increase the trust in the automation, enabling also the traceability and to detect errors very easily. Now the question comes up, where do we execute it? Well, all that CI/CD pipeline is executed on a dedicated server, either hosted on-premise or can be an external mainframe. This means the preparation for this pipeline need to be done by the tool experts that before worked with the graphical user interfaces, which are experts on their dedicated steps, creating the scripts for the automation, which will also enabling the engineers to work very independently from each other, supported by the automation pipeline using the different tools. And this absolutely allows to automate the most repetitive working steps. With this example, I want to get back and sum up what we've just discussed. Well, we've seen the different trends in the automotive industry and their enablers. For the trends, we're talking about automation, connectivity, and electrification. We need to focus on the enablers to make these trends happen. And the enablers are, for example, the EE and ECU architectures, the software that is running on top of those, and how we collaborate with each other. And to cope with the future challenges, we need to adapt in many aspects. So let's find the best way to complement each other. And we are very happy to share our ideas, and we are looking forward to help you getting that done. Thank you very much.